Great. And the main idea today is we'll be dealing with applications. And to get started, we have to be able to convert English to math. That's going to be the first hurdle that we will tackle today. Whenever you hear the expression sum means we're looking to add quantities together. When you hear the word difference means we're looking to subtract. When we have product means multiply, and quotient means that we divide. That's what those vocabulary words mean. An example using these, because this is going to come up a lot when we deal with applications, we'll have to convert English to math, and that's typically where people struggle. So let's try to practice this before we get into the word problem. What if I asked you to write the sum of a number and 6 is 28? What I'm asking us to do is, that's an English sentence. I'm asking you to convert that to a mathematical equation. When we see sum, that means we add. When we don't know what a number is, we use a variable, x. And when you see that word is, that typically means our equation. So when we say the sum of a number and 6, a number and 6 with the sum is 28, that's the equation that we write from that. And then we can subtract 6 and get x is equal to 22. One other example from this topic, what people tend to get a little confused about, is if I ask you for the difference where 3 less than a number is 8. Typically what people do is they do 3 minus x equals 8. But that would be wrong here. If I asked you what's 3 less than 10, you would tell me what? 3 less than 10 is 7, of course, right? So when you do 3 less than a number, you take that number and you subtract 3 from it. In this case, x would be 6, or x would be 11. 3 less than 11 is 8. So it's a really valuable skill that we can convert English to mathematical equations. Now that we have that done, I want to talk about applications. So we'll call this steps to solve applications. There's 3 steps, and if we apply this to every word problem that we see, we'll get them correct. Typically, people get confused when they just fly blindly into a word problem and they just start trying to throw numbers all over the place. We need some kind of procedure in order to do this. So steps to solve applications. The first step is we have to define our variable. Typically, we use x for that. you have to know what x is in order to formulate that equation. The second step is we write our equation. And then the third step is we solve. So let's go ahead and take a look at the problems today. And again, if you want, you could just write the work down. The problems are all typed out for you in the supplemental materials folder, so that way it'll save a little bit of time with writing in class. Taking a look at this first problem in section 1.3. The length of a rectangle is 5 more than its width. So we hear more, we're thinking addition. The perimeter is 5 times the width. Find the dimensions. One way that I recommend that students do these kind of problems is to draw it. Let's draw it out. And then we could label the length and the width and get a better perspective on how to solve this problem. So we'll define our variables. L means length, W means width. And if we know that the length is 5 more than the width, that means whatever the width is, the length is 5 more than that. The length equals 5 more than the width. 5 plus W. That's how we convert English to math. The length is 5 more than its width. The perimeter, P, is 5 times the width. Find the dimensions. We defined our variables. We wrote out our equations. Now we just have to go about and solve it. Well, one of the equations we have is that the perimeter is 5 times the width. Does anyone know what the perimeter is? How do you find the perimeter of a rectangle? What would you do to get there? Yeah. All right. 2 times the length plus 2 times the width. We could also just add up all the sides, right? But I like that formula better. So we know the perimeter is 5 times the width. We also know that the perimeter is 2 times the width plus 2 times the length. Right? What is your name? Yeah, thank you. So if we know that the perimeter is equal to 2 things, that means that they're equal. At this stage, we could say, okay, if the perimeter is 5W and the perimeter is also something else, we could say that 5W is equal to 2W plus 2L. There's one more step to really get this ball moving. We have 2 variables, and we didn't use this at all. We know that the length is 5 plus the W. Does anyone see how we can incorporate that into this equation? Yeah. That's right. What's your name? Emily, thank you. So Emily said we could substitute this equation in for L. And then from there, it's just straightforward algebra. Let's go ahead and do this. We have 5W is equal to 2W plus 2 times L. Those 2 equations are equal. So we saw this in our last class. We can go ahead and distribute the 2. And 5W would equal 2W plus 10 plus 2W. Let's combine our like terms. 5W would equal 4W plus 10. finish it over here. I'm running a little bit out of space. So 5W is equal to 4W plus 10. If we subtract 4W on both sides, we get W equals 10. The width is 10. It wants to know the dimensions. We know that the length is 5 plus the width. That would mean the length would be 50. Where people get hung up on this is if they just start throwing numbers all over the place, right? It's a good idea to draw out the picture, define your variables, write your equations, and then use logic to finish it. Applications are a little scary. People generally have trouble with applications. On my math lab, you could practice as much as you want. When you see your test, there's not going to be any surprises. It'll be similar to a problem we did in class or on the homework. Let's take a look at number 2. It says 2 baseball players, Mike and Barry, had 111 combined home runs. Mike had 7 fewer than Barry. Find the number of home runs each player had. So we're talking about home runs for 2 players. Let's let M represent the number of home runs for Mike. And let's let B represent the number of home runs for Barry. We defined our variables. The next step is we have to come up with an equation. It says together they had 111 combined. So what would be an equation we could write to say that together, the number Mike got and the number Barry got together is 111? Yeah. Very good. So we know that together, M plus B equals 111. We also know that Mike had 7 fewer than Barry. So the number that Mike had was, is it B minus 7 or 7 minus B? 7 fewer than Barry. B minus 7. Remember, we talked about this before. If I asked you what's 7 fewer than 10, you would tell me it's 3, right? We just kind of switch that order. So we have B minus 7. At this point, we have our equations. Like we did before, we could substitute B minus 7 in for M. We have B minus 7 plus B is equal to 111, combining our like terms. Add 7 and just use algebra to finish this. 2B would equal 118. Dividing by 2, we get B is equal to 59. If B is equal to 59, and we know that M plus B is 111, we could figure out that Mike got 52 home runs. Moving on to number 3 is healthcare. Healthcare spending saw an increase of 31.6% to $594.6 billion compared with 2010 numbers. Find the spending in 2010. First thing we have to do is define our variables. That's typically what do we want to find. Find the spending spree in 2010. So let's let X represent the spending in 2010. And it says that it increased by 31.6%. So this is where we have to kind of think this through. The amount of spending in 2010 plus the spending in 2021. It doesn't tell you what year it is. Let's assume it's last year. The spending in 2010 plus the spending in 2021 is equal to $594.6 billion. The spending in 2010 we said was X. The spending the next year, or the spending in 2021, whatever this year is that they're looking for, is an increase of 31.6%. The question is, how do we write 31.6% more than X? So 31.6 as a percent would be 0.316. And that's more than X. So that 0.316, that's an increase of 31.6% of whatever X is. We could just write this X plus 0.316X is equal to 594.6. Combining our like terms would be 1.316X equals 594.6. And dividing by the number in front of X, tells us the amount of spending in 2010 is equal to $451.8 billion. We defined our variables, we came up with an equation, and then we used algebra to solve it. Sometimes the equations are a little bit easier to set up. That would be how you do something like this. For problem number 4, it says that a woman has $34,000 to invest. Invest some money at 2.5% and the rest at 2%. Her total interest was $772.50. Find the amount invested with each rate. So it looks like we have two rates. We have one amount of money that's invested at 2.5%, and we have the rest that's invested at 2%. Let's figure out this first. Some of the money is invested at 2.5%. So let's let X represent the amount of money invested at 2.5%. Her total interest was $772.50, which means that the money for the interest at 2.5% plus the interest at 2% has to equal $772.50. Logically, that's what that's saying. We invested some money at 2.5%. We invested the rest at 2%. The way that you figure out interest is you take the total amount of money times the interest rate. If you have $100 that's making 10%, the amount of money that you made was 10% times $100. So in this case, the amount of interest we have at 2.5% is how many dollars we have times 2.5%. Plus how many dollars we have left invested at 2%. This is where it's a little tricky. If we invested X number of dollars at 2.5% and there's 34,000 total, how much is left over? That's $34,000. X number of dollars we already invested, how much is left over? $34,000 the pot, right? Say if I invested $4,000, how much is left over? 30,000. What we do is we take the pot, 34,000, and we subtract whatever's already invested. So in this case, we take $34,000, subtract X from it, and then multiply by 2%. And that's equal to 772.50. The hard part for this is coming up with those equations. Let's go ahead and solve it now. The way that we work with percents is we convert them to a decimal. 2.5% is the same as 0.025. And this would be 0.02 times 34,000 minus X equal to 772.50. We'll have to distribute the 0.02 here. If we distribute that, we get 680 minus 0.02x is equal to 772.50. I'll finish that on the side. I'm having a little out of room here. But I'll combine my like terms. 0.05 minus 0.02 is right here, 0.005x plus 680 equal to 772.50. Just combining like terms. Subtract 680 from it. 0.005x is equal to 772.50 minus 680 is 92.5. Dividing by 0.005 tells us that X is $18,500. That was the amount of money we invested at 2.5%. Remember, we said X was the amount of money we invested at 2.5%. The rest of it was invested at 2%. So that would mean 34,000 minus 18,500 is 15,500 is what's left, and that would be invested at 2%. A couple more problems left in this section. They're similar. Did anyone try to take a look at the notes online? Did they work okay? Yeah. It's cool, isn't it? Yeah. I also posted the videos. Did you guys see those too? Anyone? Okay. Somebody saw them. Did they work okay? All right. Good. I'm glad everything works the way it's supposed to. All right, let's take a look at number 5. It says a chemist must mix 8 liters of 40% acidic solution with 70% solution to make 50% solution. How much 70% solution is needed? So when we have these types of problems, it's really important to get organized. Typically, the way that I would recommend that you solve these is we make a table with 3 columns. Let's make a table where the first column is liters. The second column is percent pure acid. And then the third column is liters of pure acid. All right, so let's go through this. A chemist must mix 8 liters of 40% pure acid. 8 liters. It says 40% pure acid with some 70% solution to make 50% for the total. So just take a second and see if you can understand where those numbers come from. We have 88 liters of 40% acid. So 8 liters, 0.4 is the same as 40%. The way we get liters of pure acid is we just multiply them. 8 times 0.4 is equal to 3.2. That's how many liters of pure acid there are. For that second one, we don't know how much of the 70%. That's why X is sum. But sum of 70%, we could just do X times 0.7. That comes out to 0.7X. And it gives us the total of 50% acid. If we set it up using this chart, we just have to figure out what goes here. We're combining 2 different fluids. One is 8 liters, one is X liters. What do we write to combine? This number of X. Total, we want it to be 50%. So we just add the first one plus the second, and that would be 50%. So 8 plus X times 0.5 is equal to, so we could just distribute the 0.5. And that comes out to 4 plus 0.5X. The way that we would finish a problem like this is we know what the total is. So let's go ahead and make one equation that represents that. When you add these 2 together, the amount of pure acid from solution 1 plus the amount of pure acid from solution 2, that needs to equal the total pure acid. Pure acid from the first solution is just 3.2 plus the amount of pure acid from the second is 0.7X. And that's equal to the total, which we saw was 4 plus 0.5X. So the chart is critical in order to be able to solve something like this. It helps us get organized. If we go ahead and get our variables on the same side, so I'll subtract 0.5X on both sides. We get 0.2x, 3.2 still there. I'm going to subtract the 3.2. We get 0.2x is equal to 0.8. We divide both sides by 0.2. We get x is equal to 4. And remember what x was. X was the amount of solution 2. So if we use the chart to get organized, that's what we want to do. One more problem to finish out this section, and then we'll do some more word problems, which is what section 4 is. For problem number 6, it says how much water must be added to 20 liters of 50% antifreeze solution to reduce it to 40% antifreeze. So we're going to do the same process, but this is asking for how much water, not how much acid. It's a little different than the other problem. So again, we'll set it up with 3 columns. We'll have liters. We'll have the percent of pure water. And then we'll have the liters of pure water. It's similar to what we did before. Let's take a look at that first part. It says 20 liters of 50% antifreeze solution. So if half of this solution is antifreeze, what percent of it is pure water? What's that? The other half, right? So we would say 50% of it is pure water. The way that we get the liters of pure water is we would just do 0.5 times 20, which is 10. That's for that first one. The question is, how much pure water must be added so we get a total that's what percent pure water? It's 40% antifreeze, so how much percent would it be water? 60, right? But we have a few blanks we have to fill in. We're looking to pour in pure water. How much pure water are we pouring in? How many liters of pure water are we pouring in to get that 60% purity? Well, what would go in the percent pure water box? If we're pouring in X liters of pure water, what percent of that is water? 100%, right? We're pouring in water to dilute it. So it's 100%, which is just 1. 1 is the decimal equivalent for 100%. So I'm pouring in 100% pure water to dilute it. The liters of pure water would just be 1 times X. Now it's the same exact problem that we just did. Just like Nick said before, the total amount is going to be 20 plus X. We multiply that by 0.6. That'll give us what we get from the total. And we'll set that equal to the combined from solution 1 and 2. So 0.6 times 20 is 12. 0.6 times X is 0.6X. And the way we'll finish this is we'll say pure water from the first solution plus pure water from the second solution is equal to the total pure water. This is how we're setting it up. The more you practice, the better you'll get at this. Right? It's easy when I'm doing it and I'm walking you through it. The way you get better is by practicing. So the amount of pure water from the first we had was 10. The amount of pure water we had from the second was X. The total pure water was 12 plus 0.6X. And if we solve this equation, we'll get the total number of liters of pure water. Let's go ahead and do that. I'll subtract 0.6 on both sides from X. 1 minus 0.6 is just 0.4X. The 10 on both sides. And divide by 0.4. And that gets X is equal to 5. That's the liters of pure water. All right. So that'll conclude section 1.3. Those problems are more geometry. We're looking at rectangles. We're looking at using some formulas to figure out dilution rates. The next section will be dealing more with distance, rate, and time problems.